Hello everyone, and thanks for joining me at the SimAUD 2020 online conference. Today I'm going to talk about simulation-based design optimization for mixed-use recreational buildings with TEUI, TEDI, and GHGI targets. My name is Jeannie Chan, and I'm a building performance engineer, and I work at Stantec Consulting, which is located in Vancouver, Canada. This is the agenda for this presentation. First, I'm going to talk about the project description, then the project targets, the methodology that we use for this analysis, the performance of the proposed design, the TEDI reduction analysis, and finally the conclusions and recommendations. The project is a recreational facility with a residential tower, and it's located in Vancouver, British Columbia, Canada. It is a 14-story building and has a conditioned floor area of approximately 13,000 square meters. It has a gymnasium, a pool, fitness area, office, lobby, and residential suites. Here are the performance targets for this building. It's trying to achieve rezoning with the city of Vancouver, so it has to follow the green buildings policy for rezoning. So in this policy, there are TEUI, TEDI, and GHGI targets for particular types of buildings. Since this is a recreational building with a residential tower, these are the two categories that is relevant to this building. For the residential high-rise, it has to meet a TEUI of 120, a TEDI of 30, and a GHGI of 6. And for the recreational part, it has to meet 35% better EY than the building bylaw energy efficiency requirement, and that is ASHRAE 90.1 2016. Here's the methodology that we've used for this analysis. First, we create a proposed building energy model based on the current design documentation, and we look at the performance of the building as is. Then we look at the heating and cooling analysis to see where there are opportunities for energy savings. And then we select design measures based on that. Then we evaluate the design measures either with an energy model or the parametric design analysis. And then finally, based on the results from the evaluation, we make recommendations. Here are the key features of the proposed design. For the envelope and lighting, those are the values that are shown in this table. For the edge track central system, this recreational facility uses a heat recovery chiller and a backup gas-fired boiler. For the residential areas, a gas-fired boiler is used for heating and there is no cooling. At the zone level, the recreational facility uses a VAV with reheat system, and the residential area uses hydronic baseboards. Heat recovery is performed by the heat recovery chiller and also HRV systems. Here is the breakdown of the heating and cooling load for the proposed design. For heating, 50% of the heating load is from pool-related heating, and that is because the pool has a high airflow rate and it has a high heating set point of 28 degrees Celsius and high pool evaporative losses, which leads to high dehumidification levels. For cooling, the largest load is dehumidification and space cooling for the pool. In summary, the pool is a big energy consumer in this building. Here is the energy use breakdown for the building. As we can see, the heat recovery chiller that provides heating and cooling takes up the biggest chunk of the pie with 31%. Then it's followed by the fans, which take up 25% of the energy use, and then the backup heating from gas that takes up around 15% of the energy use. Here are the results for the proposed design. As we can see from this table, the current design meets the TEUI target, the GHGI target, and the TEDI target for the residential areas only. It unfortunately does not meet the whole building TEDI target. It's important to note that the whole building targets are area weighted, with 35% being residential and 65% being recreational. So this means that if we try to implement any TEDI reduction measures, it would be best to target the recreational area since it has the biggest impact on the TEDI. So now we will perform a TEDI reduction analysis with the objective of meeting the whole building TEDI target of 201. Also, we will try to improve the aesthetic of the residential tower while still meeting the residential TEDI target of 30. There are three categories of measures we will analyze: the recreational facility, pool space, and the residential towers. First, we'll start looking at the measures that are specific for the recreational facility. The first measure we'll look at is reducing the window to wall ratio from 57% to 40%. Then we'll look at the addition of a pool cover, which decreases the latent gain to the space, the dehumidification load, and reheating required after dehumidification. We'll also look at exhaust air heat recovery coils. That's where heat is recovered from the exhaust air via cooling coils. This does not technically reduce the TEDI, but can be argued that it does reduce the heating load. Here are the impacts of each measure on the whole building TEDI. As we can see from this graph, there isn't one measure that will make the project meet its TEDI target. So therefore, we recommend at least implementing 2 of these measures. In this section, I'm going to talk about measures relating to the pool space, but first I'm going to talk about design challenges for that space. So there are condensation issues in the winter. That is why the pool space is dehumidified to a relative humidity set point to avoid the condensation at the windows. So condensation occurs when a warm, humid air is in contact with a cold surface, such as a window. So designers have provided fans to blow warm air on the inside surface to alleviate this problem. But another solution is to provide better windows. So if you have better windows, the inside temperature is higher and the maximum relative humidity percentage set point can be higher, which leads to less dehumidification, less reheat, and a lower TEDI value. So we looked at some passive house pools to see how they reduced their TEDI value. So at the Barbados pool, they have passive house windows, which, like I said before, provide a warmer inside surface temperature, which equals to higher relative humidity set points without condensation. Another thing that they did was have relative humidity set point setbacks. So they set it at 58% during the operating hours and 64% when they were closed. So in their studies, they found that the setback had the same effect as a pool cover regarding evaporative losses. Finally, they had variable airflow rates. They had demand control ventilation with a minimum air change rate of 50% of its maximum design volume. So back to the building, based on the lessons that we learned from the Barbados pool, we decided to analyze these 3 measures. First, we're looking at passive house windows. Then we are looking at humidification setbacks at night. And then we also looked at variable airflow as well. So here are the results from our study. So from implementing those 3 measures, we were able to lower the cooling load, the heating load, and also the fan power. And finally, the TEDI was reduced to 231. So still not meeting the 201 target, but getting closer. So now we looked at the residential tower measures. We did a parametric design analysis for this to see what we can do to maximize the glazing on the east and west facade. So here are all the results. In the red area is the study parameters, so the different design parameters that we could change. And on the blue area is the results, so the resulting TEDI for the residential area. So looking at the results, to achieve a 30 TEDI value for the residential area, heat recovery is absolutely essential to the design. Then we wanted to see that with the proposed envelope, if we were able to have a 50% window to wall ratio on the east and west side. And as you can see from these results, we are able to do that without compromising the TEDI value for the residential spaces. Here are the conclusions and recommendations for this analysis. First, we looked at lowering the glazing percentage, adding the pool cover, and adding exhaust air heat recovery coils to the recreational facility. Since none of these can reduce the TEDI enough to meet the project targets, we recommend at least implementing 2 of them. For the pool area, we looked at a passive house approach and found that it can provide significant heating and cooling loads and fan power savings. And also the pool cover is no longer required with this approach. Finally, for the residential tower, we looked at several options with a parametric design analysis, and we found that an HRV is required to meet residential TEDI target, and that with the proposed envelope, 50% window to wall ratio on the east and west side is possible, and higher window to wall ratios may also be possible if thermally broken balconies are implemented. So the next step for this analysis is to look at the life cycle cost implications and the ease of implementation before making final recommendations. Thank you for your time and hope you enjoyed the presentation.